my group and Ismail's group. So I already told another group, you have a common group, you can discuss these things there. So yes, yani, this transformers I need to explain, or I have explained this one? I think I have explained this one. Check it.
Yes, you did.
Yes.
Yeah. So for the transformer, just review, because we will use this transformer later on. That's why but you know that very well how transformer works basically. So transformer is basically a electromechanical device. It's a bulky, heavy. You can see outside of your building or near to your building, basically. So these transformer which is near to your building or outside of your compound somewhere, you can see they are basically step down transformer. They used to reduce the voltages. So supply voltages usually it is 440 volts and it is stepped down to 220 volts. So this is bulky. Now when both the windings are equal, so equal voltages will be there. Then there is a change. We have discussed these things. So the main thing is this formula. Vp over Vs is equal to N over N2, right? This is something. So Vp, any primary voltage, secondary voltage, and this one. And based on that, there is one question I also ask you. So you can see the turn ratio. So 4:1. Yani primary winding is 4 times larger than the secondary. So it means is that it is a step down transformer, which is step down with a factor 4. So 120 divided by 4 will give you Vp secondary, which is 30 RMS. So here, this is the way to find it. Now, girls, so this is another application of the full wave rectifier. So actually, rectifiers, do you know what is rectifier? Do you remember? Rectifier. What is this circuit? What it does basically?
It converts AC into direct current.
All right, correct. So in the just addition here, it converts AC into pulsating DC. Pulsating. Yani you can see this one, what it is giving the output. So this is the output which we are getting. Is this a DC? If you look this output, is this a pure DC? No,
it's pulsating.
Right? Yeah, because it is the pure DC, yani a straight or constant value voltage. This is some voltage which is like fixed 5 volts, so it will be constant. But it is not constant. There are pulses, yani up down. So that's why it is DC, but it is not pure DC. It is a pulsating DC. So this is the later on we need to filter out these pulsating DC to a pure DC by applying filters. Did I explain to you via falstat.com how it is converting and all these things?
Yes, you showed us.
Yeah, with the filter, capacitor filter, right? All right. So now look, just quick review. Rectifier, which which convert AC into pulsating DC. One thing. Rectifiers are of 2 types. What are the types? Half wave rectifier and full wave rectifier. So half wave rectifier we have discussed previously. Now today we will discuss full wave rectifier. So full wave rectifiers are of 2 types. One is called center tapped, another one is bridge. So we will discuss both one by one. So in center tapped, girls, we use a transformer, which you can see here. This is a transformer. It is a primary winding, it is a center winding. And in this transformer, which is new for you, there is a center point, center tapped here. Yani what happened? The secondary voltage which I am getting across the secondary winding is gonna split into 2 parts. How it is split? It is split as VP secondary, okay, VPS, any peak voltage of the secondary you will be getting, and it will be getting here half. So half above, half below. Yani center tap divide the VP output and secondary output into 2 halves. So half you will get here, half you will get here. This is the way. And another thing, in center tap full wave rectifier, we use 2 diodes, D1 and D2, you can see. And girls, what is the working? You see now. So as we apply positive half cycle, So step down transformer, step it down, and this is positive terminal, this is negative terminal. So you can see when this A is positive terminal, so D1 will be in forward bias, because here is center point, yani it is considered to be 0. We can consider like that. So you can say this point is connected to 0, this is connected to high voltage, positive. So D1 will conduct or not?
Yes, it will.
It will, right? What about the D2? You are connecting, this is negative, and another one is you are connecting with the 0. So you can see anode is more negative with respect to cathode. So this will not conduct, yani it will behave like a open circuit, reverse bias. Got the point?
Yes.
So what happening during this positive half cycle, which is drawn here, D1 will conduct, and see how it will conduct the direction this way, we know that, and how the current will flow in the load resistance, right to left. This is positive terminal, this is negative terminal, and this way the current is flowing. So we will be getting output via D1, and this is the output. What about the D2? Khatam. Sorry, this is nothing here, right? Nothing, because it is in reverse bias that time. So this is the first step. Now guys, as the negative half alternation of the input comes, so this is positive, negative, this is positive. So D2 will conduct, D1 is in reverse bias. Got the point? And again, the arrow tells you how it is gonna be conduct the flow of current through the diode. And after reaching here, all current will pass through the load resistance. Can you see again, in both the cases, current is flowing in the load resistance from right to left. Am I right?
Yes. Yeah.
So what will happen? During this negative input, still current in the load is same direction. So both, whether D1 is conducting or D2 is conducting, both are upper half, because direction of flow of current same. Now girls, so for a complete cycle from here to here, we can have a composite waveform, and we can see that both the waveforms, and we got the half, but we got both upper half, not the below half, because of flow of current only in one direction in both the cases. So this is one cycle. Now later on you can continue another, because it's a continuous or periodic waveform, so it is continue. So this one is because of D1 conduction, another half is because of D2 conduction. So now you can compare with the half wave rectifier, girls. So in the half wave we were getting only one half, another half was clipped, third half, then fourth half is clipped. But here this is the advantage, we are getting, we are able to filter out both the cycles now, and we are getting more output. So efficiency of the full wave rectifier is double than the half wave rectifier, because you can say this is the half wave output, this is the half wave output. Now we have a composite which is double than the half wave rectifier output. Got the point? Clear to all of you?
Yes, clear.
Okay, so this is the working. And sometime, okay, how the question may come, we can give you this waveform, input waveform. We can ask you girls, draw the waveforms of the, D1, D2 and composite waveform. So you need to draw accordingly. So very important thing is, girls, this is the dotted lines. You can see this reference lines, which is very important. You can see this one, very important. So if reference is not given, you can draw it, and then you can draw properly. No one can draw this one like, okay, this started and ending here. How it is possible ending here? Never possible, because this is the positive half of the input. So output will be available during that time only. So whenever you draw, be careful. You must draw with a reference lines. Did you get my point?
Yes.
Okay, so drawing has to be clear. Maybe we can give these questions in the final examination or something like that. So you have to have a complete idea how it is working and how, basically. So girls, one more concept here, which is about how much output you are getting. As you can see, girls, this, okay, just bring your concentration to the first circuit, this one. So as I said, the output is VP secondary by 2, and you know that this is not working. Okay, because of its reverse bias. So how much voltage I will be getting, because this is our circuit now, And so definitely you understand that what I am getting, we are getting VP out, peak value of the output, which is how much it will be. Will it be VP secondary by 2 or not?
Yes.
Right? Because is if we apply KVL to this circuit, we can say there is no drop because of it is conducting. So that this complete voltage which is here will appear across this one. And this much is how much this one? VP secondary by 2. So the VP out, yani the voltage across the load resistance will be VP secondary by 2. All right. Now one more concept comes, which is PIV, peak inverse voltage. And what is peak inverse voltage, girls? Peak inverse voltage is the voltage which develops across a diode when the diode is in reverse bias. So you can see when the diode 1 is in forward bias, what happening with the D2? It is in reverse bias. So we need to find how much voltage is developing across the D2. Is it greater than breakdown voltage? If it is greater than breakdown voltage, D2 will damage quickly. We cannot reuse it. So how much it will develop, we can find it out. So next aim is to find how much is the PIV. Okay, so for the PIV, as I just said to you, this is the concept. Yani when the D1 is conducting, girls, so the output we are getting, which is VP out, and it is equal to VP secondary by 2. Or I can say VP secondary is equal to twice of the VP out, or VP out by 2. Both are possible. Now, what I said, VP out, already explained to you, VP secondary over 2, or I can say this way, twice of VP out, like this. Now look for the peak inverse voltage. So next is about the peak inverse. Okay, maybe I can explain to you peak inverse voltage with this one, or this is the same explanation, girls, how it is working. You see positive half, so D1 is working, output is available here. So same circuit, but they have here, ground shown here and ground shown here. Okay, next, this is D1, D2 is conducting, D1 conducting, D2 conducting, D1 conducting, D2 conducting, like that. It's continue. Now, peak inverse voltage, girls. Here is easy with this diagram. It's the same one, rather than they just draw, resistance like this and this one, or this one. Okay, both of them. Just a minute. Okay, just read this one. Okay, so if you just read this one, so if we apply KVL across, outer loop, girls, we can see this. This is conducting, yani it is like closed switch, and this is not conducting. So if I ask you how much voltage is developing across this diode, girls, you can quickly say, sir, it is equal to this voltage. Yani how much we have here from here to here? We have VP secondary. So PIV, peak inverse voltage, which is developing across this diode, is equal to VP secondary. So I can say simply PIV is equal to VP secondary. Or girls, if you remember, what was the VP out? VP out in terms of VP secondary, it was VP
P secondary over 2.
over 2. So can we write VP secondary is equal to twice of VP out? So I can also say
Yes.
VP out. So this is the important formula to calculate the peak inverse voltage for the full wave rectifier, center full wave rectifier. Okay, so note it down because we will ask you also to calculate the PIV. So if you know the secondary voltage, you can quickly say, sir, it will be equal to secondary. If you know the output voltage, you can say it will be double of the output voltage. Let's see some questions, how the question may come for this. So this is the what I said, it is mentioned. VP secondary is equal to 2 VP out. Now, so full wave rectifier, the average value for a full wave rectified output voltage is twice the, again this is the average value, and it is clear to you because if you remember for the half wave it was only VP out by 2, but because here output is double, so we have twice. Is it clear? For the half wave these were not present there, right? Only positive filter out, yani this we got. So what was the average? It was VP out over pi, but because we have double here, so it is the double VP out over pi because full wave rectifier, correct? So this is one formula. So they are saying find the average value of the full wave rectified output. Again, when you see this one, you can quickly recognize, girls, it is a full wave rectifier output because it has only positive alternations, and with every half it is available, so it is a full wave. All right, now see the question. So for an ideal diode, so when say ideal diode, yani there is no potential drop inside the diode. Show the voltage waveforms across the secondary winding and across RL when 120 VRMS sine wave is applied to the primary. So first of all, girls, the voltage is given in terms of RMS. So we need always VP, peak values. So do you remember the formula to get the peak values and RMS relation? Hope you remember that one. It was VRMS formula, which
Over
is
4.7.
or this one, VP over root 2. Okay, this is the formula. So from here you can get the peak value. So once you get the peak value, you will be getting around 170 volts. Understand? So now I can draw the input waveform. So input waveform is something like that, girls, because it's a sine wave, we know that. So this is V in. What is that? V in. And how much is the value? You just calculated 170 volts, correct? Now they are asking calculate the secondary, and draw the secondary wave. So for the secondary, can you find how much will be the peak value of the secondary voltage, girls, here? Turn ratio is mentioned already, 1:2. How much it will be?
It's the same, 170, 700.
170, it will be same. Then what is the role of this turn ratio? Don't you remember the formula? V1 over V2 is equal to N1 over N2. It will be same. Yes, Mariam, it will be double. So what will be the VP secondary? VP secondary, it will be something like that, double peak. You're right. This is 340 volts because of its double, correct? Now what they are asking other than this, also find the volt across RL. And do you remember the V out is the half of the VP secondary?
Yes. Yes.
So how much it will be? It is going to be, first of all, waveform will be like that or not? Output, yes, it will be like that because it will be not the this type, because it's coming out after the diode. So this is the peak value, which is 170 volt. So all the waveforms is clear to you. V in, VP out, VP secondary, correct?
Yes, it's correct.
Right. Also, they are asking what is the PIV rating.
It's equal to the VP secondary.
Correct. So it will be 360. All right. So this is PIV, and you know that breakdown voltage and the concept. So it's like that we are giving negative voltage, negative voltage, negative voltage, but there is a limit. After that, diode will break down. And do you remember this is breakdown voltage? Correct. So we have to be careful while we are connecting this diode to this circuit. The VBR, breakdown voltage, must be greater than PIV. Otherwise, diode will damage. Is it clear?
Yes, clear.
Right? Because breakdown voltage is the maximum reverse voltage. After that, diode will damage. So it should be greater than the PIV. This is something else. All right. So solution is there in the next slide. You can see. So they calculate first input peak value 170, then VP secondary double of the input, then VP out exactly 170, and see the waveforms. The very important thing here when you are drawing, over and down, see this is the synchronization. It should be like that, girls, with a reference. See this one? Yani it cannot be here there, exactly under one waveform to another one. So this is something. Calculate the VPI, PVI, PIV, it is going to be double of the VPI. This type of questions are possible, and drawing all the waveforms is also possible. But you need to use peak values rather than RMS. Be careful. All right. Another type is bridge rectifier, girls. This is again full wave rectifier, but it is a bridge because you can see it is forming a bridge. So here we use actually 4 diodes rather than 2 diodes. This is again a full wave rectifier. So here is the input, here is the output. So girls, here is again interesting. When the positive half cycle apply here, so the terminal A will be positive, terminal B will be negative for the positive cycle, right? This cycle. So can you tell me if this A is positive and B is negative, which of the diode will be in forward bias or which will be in reverse bias? Just tell me which one will be in forward bias. D1, D2, D3, D4. What do you think?
D1 and D4 will be in forward bias.
D1. What about D4? How D4 will be forward bias? This is anode, and anode you are connecting to negative.
Oh, yeah.
No, correct? So
D1 and D3.
Correct. D1 and D3. This is correct. These two will be in forward bias. These one will be in reverse bias. So now look the current flow path, girls. You know the direction of current flow in the diode. It is always according to the arrow direction. So it will be like this. After reaching here, this terminal is open. So where it will go? It will go through the load. Are you getting?
Yes.
Then from here, down. Is it correct?
Yes,
so
correct.
Here you can see the current half cycle. So if I just draw the waveforms, this is the input waveform, girls. This is the input waveform. So what I'm getting as output is this one I am getting. Okay, now negative half cycle, girls. So during negative half cycle, yani this time, this is the time. So this upper one will be, I'm just removing this one to explain the concept now again. So remove all, go now. Okay, so you can see, girls, now this is negative terminal, this is positive terminal. Now tell me which one is in forward bias, which one is in reverse bias. If A is negative, B is positive.
D2 and D4 are forward.
Okay, D4 and D2 in forward, and D1 reverse, D4 reverse. Correct. So this is the case. So we will be, and again the flow of current you can see, because this is a forward bias, so current will always flow. We know that how current will flow according to the arrow direction of the diode, like this. After reaching here, like this. After reaching here, like this. This is the way. So can you identify the again polarity of the flow of current through the load? Same, right to
It will be
left.
the same, yes.
Yeah, right to left. So because of it, what will happen? We will get
All
the positive again in the same direction. This is something. So this is a full wave rectifier, girls. Here we are getting because of the conduction of diode D1, D3. Another half because of D2, D4. So 2 diode is conducting, 2 is off, 2 is forward, 2 is reverse, like that. So complete information is now in front of you. So see, figure A, during the positive half cycle of the input. Figure B, next figure, right side, when the input cycle is negative half cycle. So this is the conduction. In both the cases, current is flowing through the load, same direction. That's why the output waveform is only in one direction, not in both two directions. So this is the full wave bridge rectifier, girls. Now, this is the composite waveform, which is exactly same as the center tapped, except here 2 diode is conducting, D1, D3, all diode, even diode. Then composite is the total output current, which you can see down. This is something. All right. Now, what next? So it is again an explanation of the same thing working. So now they are drawing, rather than drawing here, you know, they are just showing with the help of this one, so that a path can be shown properly. So how it will be working? Like this. So 2 diode is working. This is the path of current flow. So during positive cycle, during negative cycle, these 2. During positive cycle, these D1, D2, D3, D4, and so on. Okay, this is the way. Now peak inverse voltage, which is again, okay, here important thing, which type of transformers we are using this time? Are we using center tapped? No, we are using simple. Okay, so what happening here now? When 2 diode is conducting, 2 is in reverse bias. So this complete voltage, which is the secondary, will be developed across the, you know, non-conducting diode. Okay, so see, we can apply outer loop here, KVL, and girls, you can see when it is happening, when this diode is conducting, and this will conduct that time, but this will be off. So when this is in reverse bias, so the complete voltage which we are applying, which one? This one, from here to here, will develop across this one, because we are considering this is a very minor drop across the diode, consider 0. So the secondary voltage will develop across this diode. So PIV will be VP secondary, exactly same. Are you getting this point?
Yes.
And what was this for the center tap? It was VP secondary by 2, because it is, you know, making half. But this time it's completely developing across this diode, which is in reverse bias. So PIV is VP secondary. Also, can you tell me how much is the VP output for this bridge rectifier?
It will equal the VP secondary.
Absolutely right. Very good. It is exactly same. So can I also say PIV is equal to either VP secondary or VP out? Both are equal because?
Yes.
Yes.
Correct? So this is the formula which you also need to remember, because we will be asking you calculate the peak inverse voltage. So you can calculate simply either by knowing the VP secondary or the VP output, whatever. So this is the change here with respect to the center tap. Otherwise, almost everything is same. So PIV is mentioned here. You look here. VP secondary is equal to VP out. So now, so see the question. Determine the peak output voltage. Peak output. So girls, waveform is given. Peak value is given. See the turn ratio, 1:1. It means it is just a normal transformer, neither step up nor a step down. So same voltage will be developed here as a VP secondary, because turn ratio is 1:1. So VP secondary, VP out, you can simply, you can say VP secondary. How much it will be the VP secondary, girls? 25? Yes, correct. So if we need to draw this one, we can draw very easily VP secondary. So the drawing will be like this, VP secondary. Okay, it is same as this one. Now they are asking calculate the PIV rating. Okay, so easy. PIV will be equal to VP secondary. It will be 25 also. So easy, right? But this is the way. So main thing, it is so easy, but concept has to be clear. So it will not take 1 minute, 2 minutes. You can quickly give the answer of such type of questions once you have complete understanding. So this is the way to calculate. Also, we can ask you calculate the average value. V average AVG to VP out over pi. So how much it will be? 2 multiplied by 25 over pi. You can get this one also. Average value of the full wave. Okay. So these are 2-3 things which you need to find out and you can easily calculate. So guys, this is the full wave rectifier, center tapped, and the bridge rectifier. So we studied these things, and where we are going to use it, basically the major application is to design the power supply. And do you know the power supply means? You have chargers for your mobile phones, you have charger for your laptops, you have chargers for other gadgets, tablets or so ever, right? So how it works basically, you connect to the AC in your house and they convert AC into DC and then it's charge your devices. So we use these rectifiers in the design of power supplies, and related to that one you have one lab also. So we have added a lab to understand that question this time. So how it works basically, guys, it involves transformer. After transformer we use rectifier. You know what is rectifier now? Convert AC into pulsating DC. Then we use a filters like a capacitor filter to make it smooth. After getting that, we use a regulator. What is the role of the regulator? It provides constant value regardless change in the input. If input is fluctuating, yani changing between these voltages, regardless if we are using a regulator of 5 volts, so it will give you 5 volt even if the input is changing. It will provide you fixed 5 volts so that your device or your gadget will not damage. It will receive constant voltage. So these are the steps involved while you design a power supply. So see now, what are the steps? Very first thing, we can say 220 volts AC you connect, then transformer involved to step down the voltage, then we have rectifier, then we have smoothing or filtering, then we have regulator. So transformer step down high voltage AC main to low voltage AC. Role is it converts AC to AC but step down. Rectifier convert AC to DC, but DC output is varying because of we are getting something like that variable. Smoothing, we use DC greatly for the small ripples. So smoothing will actually eliminate and it just provides something like that. Now we use regulator, eliminates the ripples by setting DC output to a fixed voltage. So these are the steps involved in the design of power supply. See now. So this is what I just explained to you. You can read it down and you can understand the concept. Next, transformer. So guys, this is a real transformer. So here we have primary this side, secondary another side, and it is basically connected like that. So you know that how it works basically. So transformer, so we are just building one by one step. So first stage is the transformer. So we are applying high voltage. It is giving us low voltage, but again, it is a AC voltage. Next, we have a rectifier. Rectifier could be half wave or full wave. We can use depend upon the situation. Then transformer plus rectifier. So we will be getting output of that from the rectifier, which is if we are using bridge rectifier here, usually we use bridge rectifier. So this is something. Now, smoothing or filter. So you can see in power supply, a filter must remove or reduce that AC variation while still making a desired DC available to the load. So capacitor we use as a filter. I explained to you that one, right? So you can see now. So it provides something like that. And you know how capacitor work. So it is like charging, discharging, charging, discharging. So by putting its value larger, charging, discharging time, we can put less. So see, so we will be getting something like that. after the output of the filter. So now see the circuit with the filter. Transformer plus rectifier plus smoothing filter. So we are getting something like that. Now after we can apply, yes, it is actually not a straight line, you know, still there are minor ripples, almost it is straight we can consider. So now we need to connect a regulator. And what is a regulator role? Because there is a fluctuation here. You can see some value is changing here. So this fluctuation can be removed by applying a regulator. So this is a regulator IC. This is a regulator which comes as a IC 3-pin. So regulator eliminates ripple by setting up DC output to a fixed voltage. Understand? So voltage regulator ICs are available with a fixed typical 5 volts, 12 volts, 15 volts. Also girls, it is available -5, -12. So whatever you need, we can just connect this one. And it is something like that. We connect here output from the filter and then we get output here, input and output. Here we will be getting constant value. So many of the fixed voltage regulator IC have 3 leads, look like the power transistors such as shown in the picture. So now this is a complete DC power supply. And you can see the output here. Now which is fixed, value is fixed. If I connected 5-volt regulator, I will be getting 5-volt fixed. Now I can charge my mobile phone. Understand? So this is something you have a charger, mobile phone charger, which provides you 5-volt fix. And if you are talking about your laptop charger, which is 12-volt fixed. So regulator is applied at the final stage. Then this. So you will be learning this one in the lab. We have this time only introduce this concept there. So this is something. Maybe in Falstad, I believe there is something related to. Just a minute. Let me just check quickly. So it's so interesting. Yani, at least you know what is a semiconductor. This one, how the semiconductor is used, what is the role, and where we are using this. See this one. So here, this is full wave, bridge rectifier, capacitor, and without regulator, girls. So this is the output. Can you see the exactly same output which I shown to you? And there is a fluctuation, right? You can see it's varying between 8. This is the current, right? So if I just make it simulation speed slow, then you can see the changes. If I look here, the voltage is 3, the higher voltage is around 4 situation. That can be eliminated by the transistor. I don't know whether transistor is there or not. Let me check. It is an active device basically. Okay, bipolar transistor, Darlington pair, variator, diode junction transistors. I don't know whether we can use it. Oh no, we are looking for regulator, right? Regulator, not the transistor. Regulator. Did not try before. Let me just check it. Can you read regulator somewhere? Okay. Maybe regulators are not available here. MOSFET 555 square wave generator, schematic trigger, active filters, logic families, combinational circuit, very good, sequential circuits, analog circuits, booster, breadcrumb converter. Sure. Okay, no problem. But maybe later on you can see somewhere. So this is something, you can maybe find this one in the Tinkercad. You can understand. So this way we have done with this chapter, guys. So it's so easy. And again, the important part is that this is gonna be now assist in your quiz, and later on it will be assist in the lab quiz as well.